Welcome to the lecture on network analysis, module 3. In this module, we will discuss program evaluation and review technique, that is PERT. In the previous discussion, that is in the previous modules, we have assumed the activity time as deterministic, but there are situations where activity time cannot be assumed as deterministic, but may be random. For example, if we consider the situation of developing a new machine or a new product, then the activity time can be well defined by a random variable. The PERT technique, which I am going to demonstrate now, takes care of these uncertainties and determines the probability of project completion time within a specified date. PERT was developed in 1956-58 by a research team to help in the planning and scheduling of the US Navy's Polaris nuclear submarine missile project, involving thousands of activities. PERT was developed to handle project where the time duration for each activity is not known with certainty, but can be described by a random variable which characterizes by beta distribution. Three estimates for each activity are required to calculate its expected completion time: optimistic time, pessimistic time, and most likely time. Optimistic time is the shortest possible time in which an activity can be performed when everything goes well. Pessimistic time is the longest possible time to perform an activity when everything goes wrong. The estimate of normal time an activity would take is the most likely time. Obviously, it is the completion time that would occur most frequently, that is the mode of the probability distribution. Here, one thing would like to mention that the activity time is assumed to be characterized by beta distribution, because possibly of the following reasons. Beta distribution is a unimodal distribution. It has finite non-negative endpoints, and the probability distribution can be symmetric or non-symmetric. Now, depending on the optimistic time, pessimistic time, and most likely time, the expected time of an activity can be obtained as Te equal to To plus 4 Tm plus Tp divided by 6, where To is the optimistic time, Tm is the most likely time, and Tp is the pessimistic time. The probability distribution of the time involved in performing the activity might be characterized by any of the curves shown in the slide. It is assumed that the distribution is unimodal and the peak of the distribution represents the value of Tm. There is very little chance that the activity can be completed before the optimistic time To or after the pessimistic time Tp. Naturally, the point Tm is free to move between these 2 points To and Tp. In the first figure, T m is less than T e, whereas in the second figure T e is less than T m. In the third figure T e is equal to T m. For unimodal distributions, the standard deviation can be estimated roughly as sigma equal to T p minus T 0 by 6. Therefore, the variance can be obtained as T p minus T o by 6 whole square. In part, the main difference is that instead of activity duration, the expected time T e for the activity is considered. And with each node there is a variance. Therefore, the duration of the project is considered as the mean expected time with its variance. Now, let me define the rules for finding the variance of events. First, we set the variance of the initial event as 0, that is V 1 equal to 0. Then V j, the variance of succeeding event j, can be obtained by adding the activity variance to the variance of predecessor event except at merge points. So, we can get V j as V I plus sigma I j square, where sigma I j square is the variance of the activity I j. At the merge points, the variance is computed along the longest path, that is the critical path, and in case of two paths having the same length, we will take the larger of the two variances as the variance of the event. Now, we will show you how to find the probability of meeting the scheduled time using PERT. With PERT, it is possible to determine the probability of completion a project on schedule. If the exact probability distribution of the path is known, then it would have been better or easy to find out the probability of completion of the project in a given time. However, using central limit theorem, the probability distribution of time for each event could be considered as normal, and because of this assumption, that is assuming the normality, the probability of the project being completed by a certain date can be evaluated easily. That I am going to show now. Suppose that the project expected duration is 19 days with variance 25 by 18. Then our problem is to find the probability that the project duration would be less than or equal to 20 days. We can write probability d less than or equal to 20, where d is the due date, which is equal to probability d minus mu by sigma is less than or equal to 20 minus mu by sigma. Here mu is the mean of the distribution and sigma is the standard deviation. Since d minus mu by sigma is the standard normal vary at z, so we can write probability of z is less than or equal to 20 minus 19 divided by root over 25 by 18, which is equal to probability of z less than or equal to 0.85, and which can be obtained as 0.8 from the standard normal distribution table. Now, let me define what is the physical meaning of this statement. Means that if the job is done 100 times under the same conditions, then there will be 80 occasions when this job will have taken 20 days or less to complete it. A designer may like to know the duration of the project that will have 95% chance of being completed. If Ts be the scheduled duration date such that probability of T less than or equal to Ts is equal to 0.95, then we can write it as probability of T minus mu by sigma is less than or equal to capital Ts minus mu by sigma, which is equal to 0.95, and this gives probability Z less than or equal to Ts minus mu by sigma, which is equal to 0.95. From the standard normal table, we can find Z 0.95 as 1.64, then clearly we can find Ts equal to mu plus 1.64 into sigma. Let us now discuss what are the steps we have to follow to find the solution of a network problem by using PERT. In the first step, we denote the most likely time by Tm, the optimistic time by To, and the pessimistic time by Tp. Using the beta distribution for the activity duration, we compute the expected time Te for each activity by using the formula Te equal to Tp plus 4Tm plus To whole divided by 6. We then calculate the earliest start time and the latest finish time and the total float as difference of these two. Then we identify the critical activities and the critical path and the expected date of completion of the project. Using the values of Tp and To, we compute the variance of each activity's time estimate by using the formula sigma square equal to Tp minus To by 6 whole square. We then compute the standard normal deviate Z0 is equal to due date minus expected date of completion divided by root over project variance. And finally, using the standard normal table, we find the probability of completing the project within the scheduled time, where Z, the variable, is nothing but the standard normal variable. From this discussion, we have learned how to find the expected time and variance of each activity when the activity time follows beta distribution. We have also learned the rules of finding the variance of each event, and we have also learned the steps to follow when we proceed to find the solution of a network problem by using PERT technique. We now proceed to take some example and show how to find the solution of the network problem by using PERT algorithm. We consider the following example. A project is represented by the network shown below and has the following data. We have the activities or tasks A, B, C, D, E, F, G, H and I, and least time are 5, 18, 26, 16, 15, 6, 7, 7 and 3. Similarly, we have the greatest time given and most likely times are also given. We have to determine the expected task time and variance, the earliest and the latest expected times to reach each node, the critical path and the probability of node occurring at the proposed completion date if the original contract time of completion of project is 41.5 weeks. Using the formula TE equal to TO plus 4TM plus TP by 6 and sigma square equal to TP minus TO whole square by 36, we compute the following table. We have the activities A, B, C, D, E, F, G, H and I. Second column gives the optimistic times, third column gives the pessimistic time and fourth column gives the most likely time, and from these 3 times we can easily calculate the expected time for each activity and then the variance for each activity as shown in this slide. Now, we find the earliest times in usual notations. Obviously, we have E1 equal to 0, occurrence of the first event 1 is 0, and then we calculate the for the second event E2, E3 for the third one, and for the fourth event E4, and similarly for the fifth event E5 we can calculate straightforwardly. But for the sixth event we have 2 merged activities 3 6 and 2 6. Therefore, we have to take the maximum of 7.8 plus 20 and 20 plus 9, which is equal to 29. Similarly, for the node 7 we have to consider the activities, 3 activities 6 7 5 7 and 4 7, and from these 3 values we have to choose the maximum one, which is 42.8. So, earliest occurrence of the event 7 is 42.8 units. Now, following backward pass computation, we calculate the latest times. Obviously, we will take L7 as 42.8 and then straightforwardly we can calculate for the events 6, 5, 4 and 3, that is we can calculate L6, L5, L4 and L3 straightforwardly. For the second event, that is event 2, we have to think of the successor activities. 2 6 and 2 5, and from these we will take the minimum value, and this gives the minimum value L2 as 16.8, and similarly we find L1 as 0. To find the critical path, we calculate the slack times by taking the difference between the earliest expected times and the latest allowable times. The figure shows that the nodes 4 and 7 have slacks 0, therefore, they will be in the critical path. The other nodes obviously will be in the non-critical path, and clearly we have the critical path 1, 4, 7, which is shown by the double arrow lines, and also the expected earliest occurrence times and latest occurrence times of the events 1, 4, 7 are equal. Now, the schedule time of completing the project is given as 41.5 weeks. Therefore, the distance in standard deviation, that schedule time from earliest expected time EI is given by DI is equal to STI minus EI by root over variance I, which gives DI equal to minus 0.52. Here STI denotes the schedule time. Then the probability Z less than equal to minus 0.52, which is equal to 1 minus probability of Z less than equal to 0.52, and which we obtained as 0.30 from standard normal table. These results has the physical interpretation that if the event is repeated a large number of times, then say 100 times, then the probability of completing the project within 41.5 weeks will be as many as 30 times. Let us now consider another example. A small project consists of the following activities and time estimates. Activity 1, 2, 1, 3, 1, 4, 2, 5, 3, 4, 3, 5, 4, 5 and 5, 6, and their corresponding optimistic time, most likely times and pessimistic times are given as shown in the slide. We have to first construct the operational network, then to determine the critical path. Also, we have to calculate the mean and standard deviation of the critical path, and then from the distribution we have to find what is the probability of completing the project in more than 26 weeks. And along the non-critical path 1, 4, 6, what would be the probability of exceeding 26 weeks? And finally, to determine what is the probability of exceeding 26 weeks along non-critical path 1, 2, 5, 6. Proceeding as before, the critical path can be obtained as shown in this slide. The double line arrow shows the direction of the critical path. Here the critical path is 1, 3, 4, 5, 6. The activities 1, 2, 1, 3, 1, 4, 2, 5, 3, 4, 3, 5, 4, 5 and 5, 6 give the expected time Ti for each activity and the standard deviation for each activities as shown in this slide. Now, directly we can find the critical path without considering the forward and backward pass computation. Clearly, in the network diagram we have the 4 paths 1, 2, 5, 6, 1, 3, 5, 6, 1, 3, 4, 5, 6 and 1, 4, 5, 6. For the route 1, 2, 5, 6, we calculate the total time. Similarly, for the other routes, and it shows that the route 1, 3, 4, 5, 6 is the longest one. Therefore, definitely it would be the critical path, and the duration of the critical path is 20.2 weeks, which is the duration of the project. Now, we calculate the mean and standard deviation for the critical path. For this, for mean we calculate simply the sum of the expected times of all the activities, which is 28.2 weeks, and for the standard deviations we have the sum of the variances is equal to 3.82. Therefore, we have the standard deviation 1.954. Now, taking T d equal to 26 and Z equal to 26 minus 28.2 by 1.954, which is equal to minus 1.12, we find the probability that Z less than equal to minus 1.12 is equal to 0.136. Hence, the probability of completing the project in more than 26 weeks would be 100 minus 13.6, that is equal to 86.4%. Now, we consider the non-critical path 1, 4, 5, 6 and calculate the expected time, total expected time equal to 27.9 and the total variance is equal to 9.62. From this data, we can find the probability that Z is less than equal to minus 0.6 is equal to 0.274. This indicates that the probability of exceeding 26 weeks along the non-critical path 1, 4, 5, 6 is 100 minus 27.4, which is equal to 72.6%. Now, for the non-critical path 1, 2, 5, 6, we find Z is equal to 4.06. This shows that the probability of completing the project along the non-critical path 1, 2, 5, 6 in less than or equal to 26 weeks is 10%. So, if we consider the normal standard normal distribution table, then the probability is equal to 1. Hence, the probability of exceeding 26 weeks along the non-critical path 1, 2, 5, 6 is nil. In this module, we have discussed thoroughly the program evaluation and review technique, that is PERT. The PERT computations are essentially the same as CPM computations. The only difference is that here in PERT we consider the expected activity time, whereas in CPM we consider only the activity time. In PERT it is also possible to find the probability of completion of the project within a specific date. With these comments or remark, we end this module.